So we are continuing from the previous lecture on matrix force method, where we had introduced the method. We had learned how to define the member forces and member displacements for the case of the beam element and the truss element, and we had also seen how we can obtain the collective flexibility matrix of the entire structure. We just re-emphasized that in the force method, essentially forces are the main unknowns rather than the displacements. So the external applied loads P, their directions, they define the positive directions of the resulting displacements. If we want to get displacement at a particular point, we must definitely apply a load at that point. Only then the method will give us the displacement at that point. Let us continue from the point of the collective flexibility matrix with two examples. Let us consider one example here to illustrate the formation of the collective flexibility matrix. So this is a truss structure having a total of 5 members, a rectangular truss. We have the diagonal elements also such that they are crossing each other, however without any connection between the two cross braces. So we are numbering the members 1, 2, 3, the exterior members, and then the braces, they are numbered as 4 and 5. Let the truss be under the action of the external forces P1 and P2. And along the lines of action of the external forces, we have the corresponding external displacements U1 and U2. So we can call these U1 and U2 as the structure level displacement. So here, unlike the stiffness approach, forces have the governing role. So P1 and P2 are the prescribed forces, and the displacements along P1 and P2, they would be the displacements to be determined. The three outer members, they are of same length, so they will have the same member flexibility matrix, that is L by EA. And for the two diagonal members which have a longer length, this would be equal to root 2 L by EA, as we are showing here. So from these individual flexibility matrices, which are just one by one and very simple, we can arrange these diagonally and we can obtain the collective flexibility matrix, so that we have only the diagonal terms as the main terms, and remaining terms, they are simply zero, as we are showing here. So here we can also obtain the vector of the internal displacements and the vector of the internal forces. So both of these will be 5 by 1 because there are 5 elements, and these can be expressed as shown here in the form of the vectors d and vector small f. So please note that here we have used the lowercase symbols for the internal displacements and the internal forces. So now we are forming the vector of the internal forces also, that will be of same size, that is 5 by 1, and the components will be f1 of all the members from 1 to 5. Let us now also see an example of a beam. Here in specific, this is a cantilever beam and it has a length 2L, and we have divided into two members, member 1 and member 2, and the load is being applied at the midpoint, and this load is P1, and another load is being applied at the right end. So basically here the governing external forces are shown. So the displacements which we'll get after solution will be along the lines of action of these external forces. So here the external displacements, the positive directions are defined by the lines of action of the forces along which we are measuring them. So here the external forces P1 and P2, they are downwards, so the displacements, they are also positive if they are downwards. So here when talking of the external forces and the external displacements, the regular sign convention of the clockwise or anti-clockwise or towards the positive x or towards the positive y or towards the negative axis, that does not work. So this must be remembered. So here we have the both members having same member flexibility matrices, and then we can form the collective flexibility matrix also. The size will be 4 by 4, and basically the two individual flexibility matrices of the members will be arranged diagonally, and all remaining terms shall be made 0. We can express this in terms of the relationship between the vector of all internal displacements and the vector of all internal forces. So now we can expand these two vectors like the way we are, because there are two members, so each of these individual vectors of the displacement and the internal forces will be of size 4 by 1, and hence the size of the collective flexibility matrix is 4 by 4. Now here for the case of the beam elements, there are two internal forces for each element, and we can identify them and label them in the figure as we are showing here. So just please note that F11, this is an external reaction, so it is being shown by a solid line, and the other internal forces like F21 and F12, they are being shown by dotted lines because they are internal forces, and finally F22 is being shown by a solid line because that is external. Also note that for the internal moments we are considering anti-clockwise as positive. So this is different from that of the external forces. After the collective flexibility matrix, the next step in the matrix force method is to obtain the force transformation relationship, and this is called as force transformation matrix. So basically this is a mathematical relationship in the form of a matrix between the externally applied forces and the internal forces of the member. So here we are applying the external forces which are designated by P, and these are the main governing forces. As in the case of the stiffness method, the external displacements, they were the governing. So here the P vector is the governing force vector, and the internal force vector, that is the internal forces covering all the members, they are to be related to the externally applied force vector P by this matrix B, which is the force transformation matrix. Let us go back to the first example of the truss and let us try to derive this matrix B for that structure. So here we are writing the relationship and connecting the vector of the all internal forces with the external forces. So externally there are two forces, P1 and P2, and the size of the vector of the internal forces is 5 by 1 because there are 5 members. So the size of B matrix will be 5 by 2. Now the next question is, how do we obtain this matrix B? Now here we are taking advantage of the fact that right now we are dealing with a determinate structure. So we can define here the term Bij on the lines of the previous definitions of say Fij. From the way we have defined the matrix B, so our term Bij is basically the internal force Fi caused by the application of a unit force Pj such that all other external forces, they are 0. So this definition can be used to derive all elements of the B matrix, especially for the case of a determinate structure where this can be derived directly. A further extension is that if we want to derive a particular column, say ith column of the B matrix, all we have to do is that along the ith external force Pi, we apply a unit force and find out what forces are induced in various members. So when we arrange all these forces in a vertical column, we will get the ith column of the B matrix. For example, here we are deriving the first column. So what we have done in the structure, we have applied a unit force P1 and we are now analyzing this system. We can obtain various forces in different members by using the method of joints. So we start with the end or the bottom joint. So the right bottom joint does not have any reaction. So we can very easily find that some of the members, they have 0 forces. They are 0 force members. So once we complete this process joint by joint, we will find that only one vertical member, that is the left vertical member, has a compressive force of unit value. So now these forces, they are in various members, and if we just arrange them vertically, we'll get the first column of the B matrix. So here we are making the B matrix. This is 5 by 2, and we know that each row of the B matrix, it corresponds to a particular internal force of the member. So all we have to do is now sequentially we list all these forces in the B matrix along the first column. So basically these are the forces generated which are being now listed on the right hand side. So that gives us the first column. So similarly we can obtain the second column of the B matrix. All we have to do now is to apply a unit force along P2 now. So we make P2 equal to 1 and P1 we keep as 0. And we analyze the structure again by using the equilibrium of the joints, and very easily we will be able to obtain all the internal forces of the members, and once we arrange them along column we get the second column of the B matrix. So here we have applied horizontal force. So as a result of this there will be a reaction in the opposite direction, and now because these two forces they are forming a couple, so this will be opposed by a similar couple in the vertical direction at the two joints which are forming the reactions. So that will also be unit. Now we can go joint by joint and we'll be able to determine the forces in the various members. For example, we start with the left bottom joint and we find that the diagonal element has a tensile force equal to √2, and by the equilibrium of the bottom joint we find that the force in the vertical left member is 0. Similarly we can find the forces in all other members simply by equilibrium, and once we have this data then we can arrange all these forces in the vertical column, and that will be the second column of the B matrix. Similarly, let us derive the V matrix for the example cantilever structure which we saw in example number 2. So here, because there are 4 internal forces and 4 internal displacements and there are 2 external forces, the size of the B matrix will be 4 by 2. So to get the first column we are applying our force P1 equal to 1 and we have deliberately kept P2 equal to 0, and we are finding out all the internal forces by simple equilibrium because this is a determinate structure, so it's very easy to find these, and we have already numbered the various internal forces. All we have to now do is arrange all these resulting internal forces along a column, and that will give us the first column of the B matrix. In the same manner, to derive the second column of the B matrix, we apply a unit force along P2, that is P2 equal to 1, and we deliberately keep P1 equal to 0. And we now find out the various internal forces F11, F21, F12 and F22, their specific values, and keeping in mind that anticlockwise is positive and clockwise is negative. So we have applied a unit force, so there will be a unit reaction at the left end, and by using the free body diagram of the left part or the right part, we should be able to find the internal moments at various locations. For example, here the internal moment is equal to L, and this is hogging moment. At the left end, the moment was 2L. So once we list all these forces in a column, so that gives us the second column of the B matrix. So this is the simple procedure to obtain the B matrix for the case of simple determinate structures. We have seen the example of a truss structure, and we have also seen the example of a beam structure.